Hello everyone, welcome back to a new video in programming the finite element method using MATLAB. In this video we are going to continue our efforts in getting the equivalent nodal loads from concentrated loads on STR bars. Now of course I want to mention that this is part of two playlists, one about the finite element method and one about programming. Both playlists are going to be linked on the top right, and as per usual, my dear channel members would have access to the entire source code. However, if you are not a channel member, then don't worry, because every single line of code is going to be written in front of you, and you can just write along and you would have the exact same code as mine. So with that being said, and without further ado, sit back, relax, and enjoy the show. Okay, so now I need to define something called get equivalent nodal load from concentrated loads. So I just copy this and go at the end here and basically paste it here. But of course I need to declare it, so that's a function. And since I have a function, it means I need also to end the function, and I need to pass in the reference of the object. That's how object-oriented programming works. Now here inside it, I'm going to first of all declare that degree of freedom is going to be 6 and that the number of nodes is going to be 2. Just some facts here. Now let's get the str node and the fem node. So the str node 1 is going to equal str line dot node 1. Why am I doing this? This will become clear very soon, because I want to ask the question if the BarForce is actually on the fem bar or not. So I need some distance calculations. So str node 1 is node 1, and fem node 1 is fem bar dot fem node 1. Okay, so I have my nodes. Now before I do anything, I need to basically, so let me just put some comments here. Here I will call this some inits. Here I need to convert the BarForce into local, because the equivalent nodal loads depend on the shape functions, which are calculated based on the fem bar in its local sense. What I mean is, if you have an X force in BarForce, it's not necessarily going to be an axial force on the fem bar, because it depends on the orientation. If you have an X force in the global sense, and you have a fem bar that is horizontal in the direction of X, then yes, the X force is going to be an axial load. However, if it's, for example, vertical, then the X force in the global would be a shear on the local. So I need to take care of that, meaning I need to convert the BarForce into the local sense. Now how do I do that? I multiply by the transformation matrix. So let's fill it in basically. Let's fill the transformation matrix. Let's put here global, or I need some name for that. I don't know what I should call it. Global inputs. And this is going to equal a vector. Here I'm going to go to the BarForce.fx, BarForce.fy. I need a vector because I'm going to do some calculations. I'm going to multiply by the transformation matrix. And I have BarForce.fz and BarForce.mx, BarForce.my, and BarForce.mz. Now for the local inputs, which is what we need, I need to calculate the local forces. Now, I don't know, I could just multiply by the transformation matrix, or maybe I should make a function in the fem bar. I think making a function in the fem bar might just overcomplicate things, because I know that the only thing I need to do is multiply by the transformation matrix. I think I should transpose this. Yeah, I think I should transpose this. So now here I'm going to go for local inputs, and this is going to equal fem bar. I have a bad feeling about this. Maybe I should check if it's even inside before I do this entire brouhaha. Before I do any calculation, I should check if I even need to, if the BarForce is affecting the fem bar. However, I'm just going to continue like this. So fem bar dot, what's it called? Transformation matrix. Let's go to the fem bar beam, which is the representation of the fem bar, and it's called transformation matrix. Fantastic, I'll take it. So here, dot transformation matrix. Now I'm not going to use the entire transformation matrix because it's 12 by 12. I only need the 6 by 6 because I have only 6 degrees of freedom. So that's the only thing I need. I don't need a 12 by 12, so I can just take part of it and multiply it by the global inputs. So this should give me the local inputs from the global inputs. I think it would be a column vector. There's an output, right? It's called ENL. I forgot to declare the output because we're declaring an output that is ENL. Let me see. Now here I said my output is a 2 by 6 matrix. So I need to declare a 2.6 matrix. So I just go here very quickly. Let me put here and say init output. And here I'm going to say enl equals zeros of num nodes and DOF. Fantastic. Then, okay, here comes the spicy part. Check if the BarForce is on the fembar. Because what's the point of doing all this if it's not inside the fembar? So I think I should take this and have it here. So I say here is inside segment. For now it equals true. And here if is inside segment, then I'm going to do some stuff. Yeah, that's how it's supposed to be. That is how it's supposed to be. Now this question, is it inside the segment, is going to take a lot of questions. Let me postpone this. So here, to do, let me postpone this for later. Let's say for now that indeed the BarForce is inside the fembar. So we need to consider it. So if it is inside, I'm going to initialize some stuff and we're going to do our calculation. So first of all, I need to know exactly where the load is. So basically we have a bar, like we have a certain bar that starts here, and then there's a distance called L1, and then there is the load, and then there is a distance called L2 all the way until the end of the beam. Because I need to know the load where it is. Now those might not be equal, so I can just put it here. They are not supposed to, they can be not equal, it's not the point, but I need to know exactly where the load is. More specifically, I need to know the L1, because L2 is basically L1 minus the length, or length minus L1. So I need to find L1, the distance of the load from the start, because all the equivalent nodal loads depend on that distance. I have the relative location of the load on the STR line. So I know the distance between the load and the start of the line. But I don't know the distance between the load and the start of the fembar. So I must find that. To find this, I need to find the distance from the start of the line to the load. And I need to find the distance from the start of the fembar to the node. And then I have to subtract them to find the distance L1, which is the distance from the load to the start of the fembar. Now I can hear you. How do you know that the load is on the fembar? We already checked that. I know the check is not done yet, but we are going to check that, and we are guaranteed to have the load on the fembar, so the value should make sense. Which means now I need first of all to find something called distance segment start. Okay? Now what is the distance segment start? What I mean by this is this, so calculate the distance between the start of STR line and start of fembar. Okay? I call it distance segment start, for example. And here, that's basically Pythagoras. So it's going to be square root of str node 1 dot x minus fem node 1 dot x square. So let me just put two brackets here and square that. The y plus the z. So I just copy this entire thing, paste it twice, remove the plus, and change this to y, and change this to z. That's the distance between the fem bar and the STR line start. Fantastic. Now we're not finished. What we're doing here is we are calculating, so calculate the distance between the load and the start of STR line. So that's called distance load, and that's easy, by the way, because all I have to do is I'm going to call in the STR line dot length. I'm going to multiply this by the BarForce dot relative location. Now here we have those, so now I can find L1. L1 is easy peasy. L1 in this case is going to equal distance load minus distance segment start. Now, just in case I would get a negative value, just in case, although it should never happen, but just in case, I'm going to basically make me a safety net here and maximize between it and 0. Now, based on L1, we are going to do a lot of things. we are going to calculate Q1 and Q2. I don't know why I call them Q1 and Q2, just values. And here I would have to calculate equivalent nodal force concentrated axial. I would have to pass in the L1. I would have to pass in the local inputs of 1, because the local inputs of 1 is the X force. And I also need to pass in the fem bar. Maybe I shouldn't. Let's pass it anyway. So this would find Q1 and Q2. Those are, what is Q1 and Q2? Calculate the share of fem node 1, which is Q1, and fem node 2, which is called Q2, of the axial load. Okay? Now, since we have the share, we can add it to the equivalent nodal load. So here, E and L, but wait, this is local, right? I still have to globalize this. This is going to be harder than I thought. Let's define something here. Define local outputs. And this is going to be basically local nodal forces. I'm going to make it zeros of, I don't know, 1 and 12 or 12 and 1. That's going to be a column vector that has the local equivalent nodal forces. So now I need to take this, because later I have to take it and transfer it somehow to the equivalent nodal loads in the global sense. So I'll copy this, paste it here, and go call in for degree of freedom number 1 and add to it. So I need to use the same here, because I'm going to add to it Q1, the share of the first node. And then I'm going to copy it, paste it here. You might need to read the code multiple times. If you don't get it, then tell me. I might make an explanation video for this entire code. So wait, this is 7. So for the second node, it gets Q2, and those are the shares of the equivalent nodal loads from the axial. I need also to calculate something called Q1, Q2, Q3, and Q4. And this is going to be calculate nodal forces from concentrated shear. Because if I have concentrated shear force, it would create shear forces at the two nodes, and it will also create moments. Q1 is the shear force at node 1, Q2 is the moment at node 1, Q3 is the shear force at node 2, and Q4 is the moment at node 2. And of course, I must do this 2 times, because I can have a shear force in the direction of Y, which causes shear forces in Y and moments around Z, and I can have shear forces in direction Z, which cause force shear in Z and moment around Y. This is going to blow my mind. So I need to stay focused here. I need to give him L1. I need to give him local inputs of 2. This is the local force in Y. And I need to give him the fem bar. Once I have it, I need to basically dump this stuff here. And that's going to be 2 for the local equivalent shear, which will take Q1. And Q2 will be taking to the moment around Z, which is degree of freedom 6. Now I need to copy this and paste it, because I need to fill in node 2. Node 2 in Y is going to get Q3, and node 2 in Z, which is degree of freedom 12, is going to get Q4. Shear force in Y. I need to do the same thing for the shear force in Z. So I'll copy this. I told you this might be the crux of the entire series. Shear force in Z. And here what changes is that I'm going to take the force in Z, and I'm going to put the equivalent nodal forces of the Z in the degree of freedom force in Z, so 3, and degree of freedom moment around Y, force in Z for the second node, and moment around Y for the second node. But wait, due to axis shenanigans, because there is a difference between the axis and the bending moment, I need to put here negative. I must do the same thing for moment around X, which is torsion here. Now torsion is like axial. It will only affect the torsion at the beginning and the torsion at the end. So now we are talking about calculate equivalent nodal force from torsional moment. And here I will pass in the torsional moment, which means that and by the way, I need to define every one of those, which means now, and I think I messed up. This should be object dot, because I'm gonna program the controller to do this, which means I need to program every single one of those functions. Object dot calculate equivalent nodal force. I'm gonna pass from torsional moment. I'm gonna pass in the torsion, and when I get it out, I'm gonna apply it to the torsion degree of freedom for the first node and the torsion degree of freedom of the second node. We are not finished, because now I need to do it again for moment around y, because bending moment around y affects shear in z and moment in y. So I copied this. This is calculate equivalent nodal forces concentrated. No, this is gonna be moment. It could be y, it could be z. Here I'm passing in the moment around y. I'm gonna use those, but due to sign shenanigans, I must fill the signs. If you're interested in the video explaining to you in detail what those sign shenanigans are, just tell me in the comments. But it's not going to be anytime soon. So local equivalent to the force 11, that's that. Now we need to rinse and repeat this. So moment around z is going to affect shear around y. Yeah, so I copy this and paste it here. And here I will say moment around z. And that's another bending moment. Bending moment 2. Here, I'm going to copy this entire thing, and I'm going to pass in moment around z this time. And yeah, I think that's that. I have the local equivalent nodal forces, but I need the equivalent nodal loads, which is this dude. So I need to take the local and calculate the global from it. So here, I will call calculate global loads and store in ENL. As a matter of fact, I might copy the definition of ENL and paste it here to the output. So let me put it here. There we go. Now here in the ENL, before I do this, let's find the global loads. The only thing I need to do is to multiply this by the transformation matrix. So global equivalent nodal forces, I should call it loads by the way, fembar dot transformation matrix. From global to local, I don't need to transpose, but from local to global, I need to transpose. No blunders whatsoever, I hope. So there's the transpose here, and I multiply this by the local equivalent nodal forces. Wait, yes, and I'm not out of the woods, because I'm going to define the ENL. Instead of zeros, I could actually define it like this. ENL equals, the first row is going to equal the global equivalent nodal forces of 1 to 6, and then hit the enter key or the semicolon, and then global equivalent nodal forces of 7 to 12, and that's that. But first of all, there is an error. I did not use it, it seems. Yeah, I didn't use it because I used magic numbers here. I can basically comment this out. This is the equivalent nodal force from considered load. There are 4 functions I must program. I will postpone them for later, because now we are going to calculate the next one. So here, I'll push the enter key, and I will calculate the equivalent nodal loads from distributed loads, which is even worse. I think I should copy this. Maybe. Let's copy this for now. So I'll copy this entire thing, enter and Control V, and change some stuff. First of all, this is called calculate equivalent nodal forces from D this time, from distributed, and it has been used here, that's true. Here I'm passing the object because object-oriented. Here I'm just going to call it load. If it is inside, then we do the things. So here I have str node 1, and I have str node 2, and for a reason that will be explained in a moment, I would have to need fem node 2, which is fembar.fem node 2. This will come in handy soon when I talk about this. So I have fem node 1, I have fem node 2, I get the global inputs. That's not how the global inputs work, because the load has actually 6 global inputs. It has fx1. Let me remind you, if you go to the STR linear load distributed, it has fx start and fx end. So it has 6 at the start and 6 at the end, which means this is incorrect. So I need to take the load here, paste it here first, and now this is, maybe I should also put a comma here and copy it again, back to back. Now this is fx start, that's fy start, let me copy the start word, fz start, mx start, my start. I can see a ton of errors when I run that. And I will debug it soon. fy end, fz end, mx end, my end, and mz end. Now I have 12 values, which means I can use the full transformation matrix at its full glory here. Now I will pass it in the transformation matrix, and I will get the local loads. And now we need to do some stuff. I need to get L1 and L2, because the distributed load is, as the name suggests, distributed. So we need to know exactly where it starts and where it ends. I need, first of all, the distance between the start of the line and the start of the fem bar, because that helps me get L1. Distance segment start doesn't change. Distance load this time is distance load start, because a distributed load has a start and an end. It has relative location start and relative location end. So here I have relative location start. By the way, this is not BarForce, it should be load. So let me just change that to load. Now I have the distance of the load start. I can find L1. That's perfectly fine by taking this minus this. So far, so good. I hope you're still with me. How do I find L2? I can still rely on those values without fem node 2 to find the end of the load, right? It should be trivial. So far, it's not clear why I need fem node 2. Let's continue our assumption that I don't need fem node 2. I will shock you in the end. So to find L2, I need to know the distance from the start of the line to the end of the load, because then I can know what L2 is. Now there are multiple options. The line, the load, could be ending inside the fem bar. In this case, L2 would have a value. Or the load could be ending outside the fem bar, which means in this case, L2 should be 0. So let me find, first of all, distance segment end. So distance segment end is basically from str node 1 to fem node 2. That's the reason why I need fem node 2. This is called distance segment end. Also, I need distance load end. So I'll paste this and I'll write this to be end. And this is relative location end. So far, so good. I will write here a helper value. I'll call it load end to segment start. What does this mean? This means what is the distance between the end of the load and the start of the segment. So basically, this is this distance. From here, all the way, let me say here, load end to segment start, all the way until here. That's the distance. From the segment start or the fem bar start to the end of the load. Why? Because I'm going to calculate L2. Now there is a chance that this might be less than the fem bar length, and there is a chance that this might exceed the fem bar length. In that case, I must limit it to the fem bar length. Let's calculate it. This is going to equal distance load end minus distance segment start. Now this might exceed the fem bar length. I don't want it to exceed the fem bar length because I'm going to calculate L2 to be equal to fem bar length minus this. So it cannot exceed the fem bar length, which means it would be 0 if it's at the exceeding the fem bar length. So here, now you could put here maximum this and 0, or I could minimize this to fembar length, and I choose to minimize. So I minimize this to fembar.length. That's L2. So that's why I'm happy so far. I'm still wondering, you might still be wondering, why do you need fem node 2? Because I need distance segment end. But still you can see even MATLAB is angry. Why do you even need distance segment end? Well, it is because I need to interpolate the values if applicable. Why would I need to interpolate the values? I would need to interpolate the values because maybe the distributed load is outside of the fembar, and if it's outside of the fembar, then the starting load at the start of the fembar is different than the starting load of the start at the start of the load, believe it or not. And the ending load value at the end of the fembar is different than the ending load value at the end of the line of the load. So this is crazy, I need to do it. I mean, we're gonna use the interpolated values here, not the local inputs. So let's interpolate them. We're gonna give a for loop here, because I'm gonna go for in every one of those degrees of freedom. So for DOF index equals from 1 to 6, I have a for loop now, and I ask the question, if the distance of the start is more than the distance load start, this means that the load starts before fembar starts. This means for interpolation. We need to interpolate that. This is called starting values interpolation. Now, if the load starts before the fembar, it means there's interpolation. So let's interpolate. I need value 1, which is local inputs of the degree of freedom. I need W2, which is the ending value, which is local inputs of a DOF index plus 6. And I need the distance. This here is, let me explain this to you. I need the starting value, I need the ending value, I need the starting location and the ending location, and the difference between the start of the fembar and the start of the load. This would give me grounds for performing a linear interpolation. That is the reason, ladies and gentlemen, why I need the distributed segment end. Just because of this. I will call the distance between the fembar start and the load start dx. And this is distance segment start, which is the fembar start, minus distance load start. Then I'm going to get the W, the interpolated. This equals W1. This is linear interpolation, nothing special here. W2 minus W1, W1 divided by the total length, distributed load end minus distributed load start multiplied by dx. Okay, so W, we have W, so interpolated values or inputs is gonna off. I haven't declared my interpolated values. I should declare it, right? So here, let's declare our interpolated values. I'll go here for interpolated inputs. This equals zeros of the size of the local inputs. So whatever the size of the local inputs is, we're going to define the interpolated inputs. And here, that's going to be DOF index. This equals W. Fantastic. Now this is happening if the load starts before the fembar. If it starts inside the fembar, then the only thing I need to do is I just can use the load value itself. There is no need for interpolation. So here I will call interpolated inputs, and that of DOF index. This equals local inputs of DOF index. Okay, now we go to the end interpolation. I think I can copy this. Let me Control X and paste it here. That's the correct place to put it. And now starting values interpolation. I'll copy this entire thing and I'll go for the end values interpolation. So here, end values interpolation. Now, since we're talking about end values, I still have degrees of freedom 1 to 6. So I need to perform interpolation to get the value of the load at the end of the fem bar. This happens if the fem bar ends before the load ends. That is the reason why I needed this. No, I needed this. Now I just noticed a small error. There is an underscore missing here. So let's underscore that. And this becomes distributed load end. So the fem bar ended before it. I would have to get the same load values. dx here is going to be something similar. However, we're going to interpolate from the end. So this is going to be end. I think that's that. Yeah, that's the interpolation. Nothing changes. And interpolated values. Now there is something here. Let me see. This should be DOF plus 6, right? It's the second node. Yeah, it's the end. So plus 6. That's true. This is plus 6. That is the end. So that's that. I need to rename all of those. Those still stand, but this becomes calculate equivalent nodal force, trapezoidal axial. Trapezoidal axial. Now, since it's a trapezoidal load, there's going to be some integration. So I need the fem bar dot length. This is the integration length. L1, L2, and here, because it's a distributed load, I need the interpolated values at 0, or sorry, at 1, and the interpolated values at 6. I need the start and the end. At 7, my bad. Now I'm going to copy this. I'm going to paste it multiple times. So because it's the same thing every time. So I'll paste it here. And this time, for the y force, it's going to be 2 and 8. For the z force, it's going to be 3 and 9. For the mx, it's going to be 4 and 10. For the my, it's going to be 5 and 11. And finally, for the mz, it's going to be 6 and 12. Now we go back to our point. We need to transform this into global, and we need to put it out. So yeah, that's that. Okay, oh my God. So now we have prepared the skeleton of calculating the equivalent nodal forces for the concentrated load and distributed load. However, I still have to program 8 functions for every case of those loads. And I'm going to do this next time. Maybe I'll do 4 and next time 4. I have no idea. So yeah, that's everything I wanted to talk about today. I hope you enjoyed. And in the end, I want to give a massive coding session-sized shout-out to my dear channel members in the contributor level and the helper level, whose names are going to be shown on the screen. I want to thank you from the bottom of my heart, as the support to the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on. Especially subscribing, because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel. I will catch you in the next video. Bye bye.